Hi everyone, Professor Bob Young back at you here, and in this instructional video we're going to look at what's called linear systems of equations, substitution method for solving systems, and the elimination method, and also take a look at some special systems of linear equations. Now, a set of equations is called the systems of equations. The solutions of a systems of equations must satisfy every equation in the system. If all the equations in a system are linear, the system is a system of linear equations or a linear system. And remember, linear, all variables to the first power from previous lessons. Okay, now if you think about this, if we're plotting two lines on the same graph, there's three different things that could happen. The lines could intersect at exactly one point, which is showed in this picture. And this system is called a consistent system, and the equations are independent of one another. All right, so that's what we're really trying to do whenever we solve the systems of equation, is we're trying to find that point at which the two lines intersect the xy value, which in this case they would intersect at the point 0, -2. The second possibility is the two lines could be parallel, so they'll never intersect. So if you're trying to solve a systems of equations and the lines are parallel, there's no solution for this. So notice here they put the empty set because they'll never cross. And this system is called an inconsistent system, and the equations are independent of one another. All right, the third possibility is you can graph two lines and really end up with the same line. And in this case, there's an infinite number of solutions. All the points on that line will satisfy both equations. And this system is called a dependent system, as you'll notice below there. And notice these two equations here are really the same thing as we get farther in here, and we will see that shortly. Now, there's a couple different methods besides just graphing, which is not really the best method for solving systems of equations. The first we're going to talk about, and it's not my personal favorite, but I'll show you anyway, because sometimes it's easier to use this, is called the substitution method. In a system of two equations with two variables, the substitution method involves using one equation to find an expression for one variable in terms of the other, and then substituting into the other equation of the system. So what we're going to look at first, the first example here, it says solve this systems of equations. So I'm looking at the two equations here, and it looks like I could easily, on the second equation here, get y by itself by adding x to both sides of the equation. So I'm just going to take this second equation and solve for y and say y equals x plus 3. Now, what I'm going to do there, and why they call this substitution, is once you take the second equation and solve for y, because remember, we're trying to figure out what point, if any, is the solution for both of these lines here. So I'm going to take that x plus 3, and I'm going to put it back in the first equation for y here, thusly named substitution. What do you think? All right, so here's what we end up with when we do that. We end up with 3x plus 2 times we solved and got y was x plus 3 equals 11. And notice it says be careful of use of parentheses here, because if you don't put parentheses for what y equals there, then you're in trouble because it won't mean the same thing. So remember, y is equal to x plus 3, so that's what we're substituting. Now distribute, and we get 3x plus 2x plus 6 is 11. Collect like terms, 5x plus 6 is 11. So go ahead and subtract 6 from both sides. We'll end up with 5x equals 5. Dividing both sides by 5, x is 1. But that's not the answer yet. Don't get too happy. Now we have to replace x with 1 in one of the other equations we started out with. So I'm going to go ahead and take the easy one just because I'm lazy. Remember, we had y equals x plus 3 there. So I'm just going to plug the 1 we solved for and got for x back in here for y. And that gives us y equals 4. All right. So the solution set here would be the ordered pair 1, 4. And you always want to write your answers to systems as ordered pairs. Remember always to write them in terms of x first, y second. Now, will these check back in both of the original equations? Notice if I put 1 in for x and 4 in for y, I get a true statement. It makes perfect sense. 3 times 1 plus 2 times 4 equals 11. Yes. If I plug 1 in for x and 4 in for y here, x changes sign, becomes negative 1 plus 4 is 3. So this point will satisfy both equations in systems. So substitution is one way to solve linear equations. Now the other way is called the elimination method, and it uses multiplication and addition to eliminate a variable from one of the equations. Sometimes in lecture classes I like to use the terminator as a reference. We're going to terminate one of the variables to get to the other. So when the terminator sees you, this is actually called the eliminator. All right, so to eliminate a variable, the coefficients of that variable of the two equations must be additive inverses or opposites. To achieve this, we use properties of algebra to change the system to an equivalent system, one with the same solution set. The 3 transformations that produce an equivalent system are listed here. Okay, so here's what we're going to look at. Interchange any 2 equations of the system, multiply or divide any equation of the system by a non-zero real number, and replace any equation of the system by the sum of that equation and a multiple of another equation. But let's start out real easy here. I know there's a lot of terminology I'm throwing at you here. Let's say we want to solve this system by elimination. Now, what I look at is, do y'all want to take out the x's or take out the y's? Do you want to be x haters or y haters? Which one do you want to eliminate? Now, I'm kind of looking at this one and saying, well, gee, Young, if I just add these 2 equations together, the y's will what? Be eliminated. And what will that leave me with? 5x equals 10. So how nice was this one? The y's were self-eliminated. Divide both sides by 5. X is now 2. So that's the first part of the answer. Now to get the y part, we have to either take this 2 for x, and let me go with some different colors here, and we can plug it in either of these 2 equations up top here. Now, which one looks easier to you? Well, kind of the second one looks easier to me. I don't know about y'all. So I'm just going to, and you can plug it in the first one and get the same answer. If you don't believe me, you can stop the video and it'll come out the same. So 2 times x is 2 plus 4y equals 12. So we'll end up with 4 plus 4y equals 12. Subtract 4 from both sides. 4y equals 8. Divide by 4. Y equals 2. So we're going to write this answer, and you can hear my puppy Lucky growling at something in the background here. You just never know what you get on these young videos. So the ordered pair XY would be 2, 2. And again, you could take 2 and plug it in for X up top here and Y. 2, plug it in for X and Y here, and it will check in both of them. All right, let's try another example here. Notice example 3. Fractions. Sometimes students get afraid of fractions here. Now again, we've already talked about this in previous lessons. How do you get rid of fractional equations if we don't want to mess with them? We are going to multiply through the top equation by the LCD of, you got it, 6. And that will give us an equivalent equation using the multiplication property. So I'm really not changing anything here. I'm just getting rid of those fractions because I don't like them. In the second equation, I'm going to multiply through by the LCD of 24 to get rid of the fractions, okay, which again is using the multiplication property. So the top equation, running the 6 through there, 6 times a half x is going to be 3x, minus 6 times a third y would be minus 2y, equals 6 times minus 3 equals minus 18. So make sure that 6 gets multiplied through both sides. The second equation, running the 24 through there, 24 times 1/8x is going to give us 3x. 24 plus 1/6y will be plus 4y. And of course, 24 times 0, 0 doesn't matter what you do to him, you get 0. Now looking at these 2 equations that's left over, nothing is going out like that previous example. I mean, if I add these two equations together, the x's, I'll end up with 6x plus 2y, and I'll still have x's and y. So this is what I mean by elimination. Now, here's what y'all have to think about. Do you want to be x haters or y haters? So what we're looking at here, if you're an x hater, you're going to multiply one of these two equations through by -1, noticing here that you've got a +3 and a +3 here. So you need to change one of those 3's to a negative to eliminate the x's. If you're a y hater on the other side of the coin, you could just multiply the top through by a +2. And you see that would give you a -4 there, and then the y's would go out. So you have your choice here. You can be an x hater or a y hater. I'm not sure which one y'all are thinking about now, but I'm going to be an x hater, and I'm going to multiply this top through by -1 to force those x's, the coefficients, to be opposite signs or additive inverses, as we said in that previous example. So what we're going to end up with is -3x plus 2y equals 18. Oh, and watch those signs there. If you just miss one sign, it's all over. And then the second equation, we're just going to leave alone. 3x plus 4y equals 0. Add these together, we get 6y equals 18. Divide by 6, y is 3. Now, to get x, you can plug that 3 in a whole bunch of places. You could take and plug the 3 in here, because we got equivalent equations all the way across here, here, wherever you see a y, or back in the original one with fractions, which I don't know if y'all would like to do that with fractions or not, but you're certainly welcome to, and you'll get the same x value no matter what. So I think I'm just going to take the 3 and put it in here to get x, now that I've solved and got y. So we'll end up with 3x plus 4 times 3 equals 0. 3x plus 12 equals 0. Subtracting 12 from both sides, 3x equals -12. And then x will be -4. So when you write this ordered pair here, you want to write this answer as -4, 3. Now, what if you put 3 -4? It won't check. And again, that should check in both cases. All right, one more example here. Now, this is probably the toughest of the tough, although I didn't put fractions in here. Y'all say, well, this one ain't as tough as the other one. You don't have fractions. Well, this one, you're going to have to multiply both equations through to get rid of x or y. So in the first example, the y's went right out, and we solved for x. In the second one, we had to multiply one equation to get rid of either x or y. This one, we have to do both. So do y'all want to be x haters or y haters? If you're an x hater, I would multiply the first equation by 2 and the second by -3. Or you could put -2 and 3. Or if you're a y hater, look at those numbers there. You can multiply by 3 the top and by 4 the bottom, because you'll have opposite signs to take out the y's. Now, which do y'all want to take out, the x's or y's? Most students will say the x numbers are a little smaller, so we'll do that. So x haters now, let's take out, well, I'll take out the x's, it doesn't matter. We'll multiply this by 2 and this one by -3. You see why I chose those? To take out the, now you could have made the top -2 and the bottom +3. See, so as long as you get those coefficients opposites, you're okay. So multiplying, using the multiplication property, the top becomes 6x minus 8y equals 2. Oh, lots of examples today. The bottom becomes -6x minus 9y equals -36. Add them together, the x's are gone. You get -17y equals -34. Divide by -17. And our first value here, y, is what kind of 2? Positive. Oh, watch those signs again. Now, where do you want to take that 2 and put it? In here, in here, in here, or in here. It does not matter, ladies and gentlemen. I'm going to be lazy again, looking at those 4 equations, and Young's going with this one. Young, you're so lazy. So 2x plus 3 times 2 equals 12 to get x. 2x plus 6 equals 12. Subtract 6 from each side. 2x is then 6, so x will come out to be 3. So the ordered pair 3, 2 should satisfy both equations up top. And I think if you plug it in, it will make perfect sense. Now, what would the graph of these two look like? Notice if we did this the graphing method, and we've graphed lines before here, the blue line is the graph of 3x minus 4y equals 1. The red line is 2x plus 3y equals 12, getting some points there and so forth. And notice they certainly do cross at that point 3, 2. So just another way to show you that what we're doing here. Now, the next one is you're not going to like as much because this is what's called an inconsistent system. Now, if you're looking at this one, you're going, well, if I'm an x hater or if I'm a y hater, if I want to eliminate x or y, well, you could multiply the top either way. I think you'll see the number by 2, and that'll certainly take out either x or y. So let's see what happens here. So we'll end up with 6x minus 4y equals 8. And the bottom we're not going to mess with because that one, all we needed to do is multiply 1 to get rid of some variables here. But Houston, we have a problem. In this one, both the x's and y's went out. And whenever you add something to its opposite, you get 0 equals 15, which is a false statement. So whenever this happens, when the variables go out and you're left with something that you're going, that's my Scooby-Doo voice, false, and you're asked to solve the system, it is inconsistent. There is no solution. The empty set is the answer. So this is called an inconsistent system whenever that happens. And notice here, if we were to graph these things, then 0 equals 15 is false. As I said, the system is inconsistent, has no solution. As suggested here by the graph, that means the graph are, guess what kind of lines? Parallel. There will be no point where they ever cross. All right, now, solving a system with infinitely many solutions. All right, so looking at this one, I might look at this and say, no matter which I go after, x or y's, I'm going to have to multiply this bottom equation by 2 to take out either one. Hopefully you'll all see that. And then we'll leave the top alone. We'll get 8x minus 2y equals negative 4. The bottom will get negative 8x plus 2y equals 4. And you might say, wait a minute, young, the x's and y's are going out. Wait a minute. It's one of those inconsistent systems, no solutions. But wait a minute. This one comes out 0 equals 0. Which, unlike the other one, is not a false statement, but a true statement. And whenever this happens, you have the same line. It's called a dependent system. Now, in intermediate algebra, all they do for the answer is you can put either one of the original 2 lines as the answer. You can put 8x minus 2y equals negative 4. You could have put the other one, and that's good. But in college algebra, I'm going to go on and show you how they write it in the big leagues. So since the result of this is a true statement, which indicates the equations of the original system are equivalent, any ordered pair that satisfies either equation will satisfy the system. So from the second equation, notice we're just going to go ahead and solve the equation for y by adding 4x to both sides of the equation. All right, we're almost done here. Now it says the solutions of the system can be written in this form now of a set of ordered pairs x and 2 plus 4x for any real number x. See, so since that's the same line, now remember here was our original problem here. Let's take something easy here. Let's put 0 in for x. Y, would you see, would come out 2 plus 4 times 0, or 2. And notice that point satisfies both of these equations since it's the same line. So what we did is we got all variables in terms of one variable here. We got everything in terms of x. And then We could also plug in some more x values and get 1, 6, 3, 14, negative 2, negative 6, which would all be on this line since it's dependent. And here is how you write it in college algebra, all variables in terms of one. So dependent systems in college algebra, they'll get everything in terms of one variable. Now note, in the algebraic solution for this last example, we wrote the solution set with the variable x being the arbitrary variable. We could have also used y as the arbitrary variable, and we would have gotten this answer. So by selecting values for y and solving for x in this ordered pair, we can find individual solutions again. And notice 0, 2 also works in here. So you will either get every variable in terms of x, every variable in terms of y, and so forth. Those of you going to college algebra. The intermediates have it a little bit easier. So this is Professor Bob Young signing off, Systems of Linear Equations. Enjoy.